Hey everyone, this is week 6 of CS 109, which makes this the fifth discussion section together of CS 109 at Stanford. Today we are talking about expectation and combinations of random variables. So things are getting more interesting. For the first question, I wanted us to talk about this last one first, actually. This last question was about binary trees. So it actually gave us a bit of code for this first question. And it said, say you had like a struct node, and you've got a left pointer node, pointer left and node right. And then you've got some code, and the code is a pointer to a function, random tree, and it inputs a probability, float probability. And then what it does is it has these two branches. It says if rand of this probability, then and it tells us what that means. Just returns it is true if it's within that probability. And then if so, right, then we have make a new node, new node is assigned. You make it new node, and then you basically make two children. Make left with a recursive call, recursion, and then make right with recursion. And that's all we got. And then basically just return new node. So this guy, right? And then what we do is we say, well, if that didn't happen, then else return null pointer. Null, effectively. Okay, great. So this is our code. And the trouble is when we are trying to ask the question of how many nodes will we end up with, we run into a snag because we have this recursive call. Basically, if this statement is true, we take the branch, or we take the if branch, right? And then we're in the situation where it makes a new node for sure, and then it branches left and branches right. But the branch left and branch right is its own invocation of the same function. So any ideas on how to approach this? So the question asks, X is number of nodes created. And then it's asking us to evaluate what is the expected value of X. Any ideas?
It's equal to the expected value of like the number of nodes in the left and right subtrees.
Okay, you're on the right track. One of the ways we can think about this problem is formulating it in terms of whether we take the if or the else first, right? And what I mean by that is this expression can really be thought of as the scenario where we take the if times the probability of that if, right? And the scenario where we don't take the if times the probability of that scenario. And what that's going to leave me with actually first is it's going to be expected value of X given the if. We'll say that if is an event. We'll just call it, I could have called it E, but I'm just going to call it if for now. So a little bit of use of notation, but I qualified it first. And times probability of if, right? Plus what? Expected value of what?
Would it be else, X given else
Yeah,
times
exactly.
the probability of else?
Or if complement, same thing, times the probability of else, right? If complement. Or else, same thing. All right, so now we have this situation. We should know that this probability of if, that's just going to be denoted as P, right? This number here. And this is going to be 1 minus P, right? So already we got two terms knocked out. And then our lives are made easier by the fact that this x given if complement, well, how many nodes are there if I know right off the bat I just go here directly? Anyone?
Just one.
Nope, it's actually 0 because no node was made.
Oh,
When I invoke this, I don't even return a node, I return null. So this is actually going to be 0. So that disappears, and because that's 0, that disappears. So I'm really just left with this, and I'll rewrite it. Expected value of x given if times the probability of if, which is just p, right? The trouble, I'm going to move this p over. The trouble is, what is that expected value of x given if? This is a really pons asinorum part of the proof, right? Or the demonstration, right? How do we get this to evaluate into something that we know how to deal with? So you have to approach this sort of intuitively and say, well, if I know that I'm in the if, right, and I'm trying to count how many nodes will I have now, right? What that actually turns into is, well, when I look at that code, I know that for sure I'm going to have one node, for sure. I'm going to have this, right? So expected value of 1 plus, and then another thing I know is I'm going to have a whole left tree. And then the last thing I'm going to know is I'm going to have a right tree, right? Plus L plus R. But what is L and R? Like, how do I grapple with what those things are? Any ideas? How many nodes will I have in my left tree? And how many nodes will I have in my right tree? Well, because my left tree is just the exact same tree that I started with, right? In other words, I invoked the same function with the same parameter. It was still with p, right? If you look at the actual code, it invokes it with p, right? I shorthanded it here in the code, but right? Since I'm invoking it with the same parameter, then that means I'm building a whole new tree. And so that is actually just going to be x plus x. So I'm going to have 1 plus x plus x. Then what I'm going to have is p of 1 plus 2 times the expected value of x. I just got that from linearity of expectation. All right. And now we've got an expected value on the left and an expected value on the right. And here's the critical move, right? It's not sufficient to just deal with what we have in the right hand, since we encounter another expected value on the right because it was a recursive function. So we kind of expect that this term would show up on the right side, even though we started on the left trying to evaluate it. And for that reason, we do some algebra, and then we end up with the expression expected value of x equals p over 1 minus 2p. And that's our final answer. Any questions on that?
I am wondering what is going to happen if p is 0.5 or larger.
Exactly. So if p is 0.5, does anyone know exactly what happens or why this is a problem? If we look at the equation, if p is 0.5, then this denominator will be 0, right? Which means this whole thing is undefined. Why p 0.5 makes this whole thing bad, right? In fact, in the question, I didn't mention it verbally, but in the question, it says the p must be less than 0.5 and greater than 1. So why is that? Well, intuitively, actually, if you think about this problem, we're constantly making more nodes, right? But the chance of us like making another branch, right, is if it's less than 0.5, then we would expect it to fizzle out eventually. It'll stop branching multiple times. Does that make sense? And eventually, it'll not produce any more nodes. But if p is 0.5 or greater than 0.5, we could be in a scenario where it branches forever. And that's really problematic. So 0.5 is the critical area where that happens. And greater than 0.5, you'll get actually like negative probabilities here, which don't make sense. You can't have a negative probability. That violates one of the axioms of probability, right? So for that reason, p is actually bounded here to only be a certain number. And if you try to run this with a p at 0.5 or greater, you could end up in a really bad case, a really bad scenario where you kind of go on forever. Okay. Going to jump to some of these logic ones, but we don't have too much time left, so I'm going to kind of speed through. So we have some logical notation. We say x independent of y. This is our notation for independent. implies covariance is 0. Covariance between them is 0. Was this true or false? This was true. This is just kind of like one of the facts that we learned in lecture. But we also mentioned, I believe, that the converse is not true, right? Just because the two random variables have a covariance of 0, that does not necessarily mean that they are independent. So that's something worth keeping in mind. Another interesting one was the variance of x plus x equals 2 times the variance of x. So this is false. And the reason it's false is this turns into just variance of 2 times x equals 2 times the variance of x. Well, this is going to turn into 4x if you remember the rules of having a coefficient in front of your random variable. So that's just going to be 4x equals 2 variance of x. And that is just a contradiction, right? This cannot be true. So that's false. But we've been in other scenarios where, for example, say I had 2 random variables, and I'll sort of end with this. Say I had 2 random variables, x1 was distributed as like a normal, right? With some parameters. And let's say x2 was distributed as normal with the same parameters, right? And then I ask you the question, what is the variance of x1 plus x2? This is trickier, actually. This is a different case. X1 and x2 are not the same random variable. They just have the same parameters, right? So in this case, we actually can't reduce it further. So if I give you another little tip and I say, well, okay, let's say that these are random variables, they have the same distribution, but they're also independent. If I told you that, now we can actually break this down further. And if they're independent, then this will turn to variance of x1 plus variance of x2. And since they have the same variance, right? Like I told you explicitly, they have the same variance then. This is effectively just 2 times the variance of x1, right? Or I could have done x2 there, wouldn't have mattered. And this is 2 times the thing, right? 2 times this quantity, which we saw in this other equation, which was totally different. So the important thing to keep in mind here, which is very critical, very crucial to grasp this, all right? If I have 2 random variables and they have the exact same distribution, that does not tell me anything about whether they are the same random variable or whether they're independent or anything else. If I just know they have the same distribution, I don't know enough about them to assess what their joint distribution is. I have no idea what their variances would do when they add. I wouldn't know very much. But if I tell you then, actually, not only do these random variables have the same distribution, but they are the same random variable, right? Well, then they add up in this certain way. They're completely dependent, right? They're like completely positively correlated with each other. Whereas alternatively, if I told you that these random variables are completely independent, right? Well, then they add up in a somewhat different way. And then when I compute things on them, like for example, adding the variances, I'm going to get different answers, right? So that's really important to acknowledge as we venture further into our journey of probability. I will stop the recording now, and thank you for your attendance and participation. I will see you folks next week.
Thanks, Tim.
Thank you.